Podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do a little math for you. We're also going to take the time to derive conservation of momentum. So momentum problems are fairly simple. We're going to do some delta P is zero problems. So this requires that we analyze a system as opposed to just one object at a time. And so we like sample problem 2 on page 315. So if you'd like to follow along in your textbook, that's where we are at. And it says a steel ball with a mass of 2 kilograms is traveling at 3 meters per second west.
Collides with a stationary ball that has a mass of 1 kilometer or 1 kilogram.
Mm-hmm.
Upon collision, the smaller ball moves to the west at 4 meters per second. What's the velocity of the larger ball?
Okay. So we have a second object of 1 kilogram. We do not know its initial velocity. That is unknown to us. Oh, no, I'm sorry. I lied. We do know that it's 0. I'm sorry.
Right. It's after the collision. We don't know what the
larger one.
What the velocity is.
So
Right?
they tell us that the small one, so that M2 is going to have a final velocity of 1 meter per second to the west. And we are in search of V1F after the fact. So as Mr. Sadler and I were reading the problem, I took the opportunity to write everything down that I knew. Like the mass of the object and the different velocities, and then in my opinion, most importantly, what is it that I'm looking for? So how fast and in what direction? This is a momentum conservation problem. And bear with me as I take these 2 steps. I always write these out as a reminder that, okay, the momentum is not going to change in the overall sense, and that the initial and the final are exactly the same. I have 2 objects, okay, so that the initial momentum of object 1 and the initial momentum of object 2 has to equal the final momentum of object 1
Plus the final of 2.
2. And so I start looking around and I notice something. I notice that the initial velocity of object 2 is 0,
Right.
which means that the initial momentum of that object is also 0.
Correct.
So I'm eliminating terms and symbols before I have to do anything else. Okay? Now I start supplying some equations. All right? So really the physics ends right here. And now I'm substituting and I'm going to be doing some algebra. You're going to see that I prefer symbols over numbers. I'm less likely to make a mistake with a symbol than I am with a number or a decimal point or something like that. So I'm going to go M1 V1I is equal to M1 V1F plus M2 V2F.
Correct.
Okay. The only thing I don't know is this guy, V1F. So my goal is to solve for that, and I can see by highlighting what I don't know, I can easily subtract away M2 V2F. Okay, and I'm left with something that looks like this. And if I want to isolate V1F, then I just have to divide the mass away of M1. And so I rewrite that. I'm going to go to another screen. And I realize that I have all of these numbers. I just have to go out and find them. I could do more to this algebraically if I wanted. I'm going to choose not to do that. I think it's in a pretty simple form. I mean, as simple as it can be at this point. So I identify M1 is 2. And V1I is 3 meters per second.
M2 is 1.
M2 is 1. The final velocity of it is 4.
Right.
And does it tell me what direction? Oh, to the west. Okay. And we divide that by 2 to get V1F. And so I hack all that out. And in this particular case, let's do the numbers here. So it's 6 minus 4 over 2. 2 divided by 2 is 1. meter per second is the final velocity of the first object. Now, they were very specific in the question statement about west. And then in their solution, they didn't get too involved in it. What if one of the marbles had been going east and the other one was going west? How would I take care of that?
Positives and negatives.
I got to go positives
Right.
and negative signs. So you want to be aware of direction, and if you have opposite directions, you're going to have opposite numbers. One's going to have to be positive, one's going to have to be negative. Now, in this particular case, if I were to try and draw this out, okay, so west would be that direction. Okay, here's object 2. Here's object 1. Okay, it's rolling along. It's going to smash into object 2. So clearly object 1 has more momentum because of its larger mass and its larger speed initially. And it's going to transfer some, not all, that momentum to object 2. So the final direction of 1 is still going to be to the west. It's important to have a complete correct answer that you include something like direction, like units. You got to have units, you got to supply direction in physics as well. Does that make sense?
Absolutely.
Okay. Now remember, if you got opposite directions, you got to have opposite values in your velocities. It's just something to look out for as we move forward and do some homework problems.
I think it's nice how you've drawn a picture to give me some idea of what the final velocity should be too.
Right.
If the large object is hitting the small object, or if the small is hitting the large, what make sure that I have some idea of whether or not my answer is actually in the ballpark.
Right. So this was 3 meters per second. So sometimes when you write down your information, we talked about writing everything out. Sometimes it's worthwhile to draw a picture, and then you could even do the after. Okay, well now they've hit, and we can talk about M2 versus M1, and we just said, okay, well that thing's going 1 meter per second to the west, and this guy is going 4 meters per second to the west. I like momentum problems because you can verify all this. You can go back to this original problem statement, and you can say, okay, 2 times 3 is 6.
Right.
Okay, and so just up here on the left side, I've got 6. Let's see, M1 times V1F. So 2 times the 1 I just found is 2, plus 1 times the 4
Right.
that was given to me. Well, I wrote the number down wrong. There we go. And so 2 plus 4 is in fact 6, and momentum is conserved, and all is happy.
Now I've double checked to make sure that my answer actually makes sense.
It's definitely a nice way to do a problem, at least in my opinion. The only other thing we wanted to talk about today is, where does delta P equals 0 come from? It's a worthwhile question. And you're about to see into the mind of a genius. This is not me, of course. This is Sir Isaac Newton. And we mentioned last time that Newton had some concept of what momentum was when he was trying to define the Newton's second law, and he was trying to work some things out. Now, Newton went the other way. He went from momentum conservation to the third law, okay, and to the second law, but we're going to go in the opposite direction, okay? We know that Newton's third law says this: for every force, there's an equal but opposite force.
Correct.
Okay. We also know, okay, that the force is equal to ma.
Right. Second law.
Second law. Okay. So remember, we're not talking about the same object. We're talking about bat pushes on ball, ball pushes on bat. So different masses and therefore different accelerations. We also know that acceleration is the change in velocity of that object over the change in time. Now, the time that these objects are in contact with each other is exactly the same.
Right.
So I don't have to subscript that out. All right? And that starts to make things a little messy. But if you're careful, you notice that we have delta t terms on both sides of the equation, don't we? So what do we get away with? We get away with canceling them. And in the next step, I'm going to get rid of the delta, and I'm going to start talking about V1F minus V1I And I'm going to start talking about V2F minus V2I. And I'm going to distribute my m's through, and I'm going to start distributing negative signs through. And if we want to start talking about initial and final momentums, we got to get all the initial things on one side, now the final things on another side. Okay, so let's see if I can do this easily. Yeah, I can add M2 V2F to both sides. Okay, and I can add M1 V1I to both sides. Okay, and so let's see, that goes away and that goes away. And what am I left with when I do some addition? I'm left with M1 V1F plus M2 V2F. So the final momentum, right? Final speed, final momentum is going to be equal to M1 V1I plus M1 V2I. The initial momentum, right?
Right.
So what is this? This is P1F plus P2F is equal to P1I plus P2I, or the final is equal to the initial,
Which is conservation of momentum.
which is conservation of momentum. And if I take the final step, it would be the change in momentum is 0. Whew. Newton worked from the bottom up. Okay, he worked from momentum conservation to the third law. We worked from the third law through the second law, a little bit of kinematics from chapter 1, and then we did a lot of algebra. Okay, so let's see, if we were to work this out, there's a lot of physics here. Okay, and then we have a big chunk of algebra, a huge chunk of algebra, and then all of a sudden we get more physics down here. Math is an integral part of doing this science.
Right.
Okay, so we're going to leave you with those profound thoughts of a genius, Sir Isaac Newton. So signing off, this is Mr. White.
And Mr. Sadler.